Okay, so this is what, lecture 20. Let's continue with the math discussion. So we discussed complex numbers and complex valued functions of real variable yesterday. So I want to talk about probabilities. Okay, so this is going to be a math lesson or review on probabilities. So that at least we'll have a common language that we can use. If I say something like normalization, you would know what that means and how to compute it. If I say something like first moment, or if I say something like variance, you would know, right? So we will be able to talk the same language. So let's start with an example. Let's say you have a room and there's 7 people in the room. And I built a histogram, or I construct a histogram of ages, okay? So before the histogram, I can say that there's 7 people, n equals 7. And this is age, and this is number of people of that age. So there is one person of age 15, 0 people of age 16. Of age 17, there are 2 people. There are 3 people of age 18, and there is 1 person of age 19. All younger than you, I think. Okay, so this is what I'm going to plot. I'm going to plot the histogram of ages. There's 1, 2, 3, 4. And here's 15, 16, 17, 18, 19, 20. And let me draw the histogram. Okay, so you have 1 person of age 15. There's nothing of age no one of age 16. There are 2 people of age 17. Okay, so this bar is twice as tall. And then there are 3 people of age 18. So this bar is 3 times as tall. Okay. Okay, so 1, 2, 3. And 1 person of age 19. Okay. This is 1 person of age 19. So that's what it looks like. So this is age, and this is number of people of that age. Okay, so first, what kind of statistical information can we try to extract from this? Well, let's try to compute average age. Let's do it just very straightforward way, right? So first, what do? You just sum all ages, divide by the number of people, right? So your textbook, I think, uses a bar. Okay, I will try to use that bar notation also. So it's 15 plus 17 plus 17 plus 18 plus 18 plus 18 plus 19. 1, 2, 3, 4, 5, 6, 7. All divided by 7. And we can crank it out. We can get the answer. But there's a better way of doing this. Let me rewrite that like that. So this is 15 times 1 over 17 plus 16 times 0 plus 17 times 2 over 17 plus 18 times 3 over 17 plus 19 times 1 over 17. And why is it useful to organize it like this? Well, 1 over 17 is a probability that age equals 17. In other words, if you walk into that room blindfolded, you grab the first person, you tap them on the shoulder. The probability that the person whom you tapped is age 17 is aged 15. That probability is 1 over 7. The probability that you've tapped the person aged 16 is 0. There are no people aged 16. The probability that you've tapped a person aged 17, well, it's 2 out of 7. Now, probabilities is somewhat hard to think of. We're not really designed to think of probability. So what do I mean when I say probability that when you walk in blindfolded and you just grab a random person, that you grab the person, that the probability that that person is age 17 is 2/7. What does that mean? What does it mean to say that? Now, there are several perspectives on probabilities, several sort of schools of thought to think of probabilities. But one school of thought is called a frequentist perspective. So what does that mean? That's a big word. What does it mean? It means that you imagine an ensemble or lots of mental copies of that experiment. So you have not just one room, but you have 1 trillion rooms. And you repeat that experiment 1 trillion times. You walk into the first room, you grab the person. Okay, you walk into the second room, you grab the person. You walk into the third room, the person. And then you count how often that person was 17 years of age, how often that person was 16 years of age, and so on. And you will see that in 2/7 fraction of the cases, what is 2/7? 2/7 is 2/7. That's 28.5%. In 28.5% of an ensemble of those experiments, that person was 17 years of age. What's the probability that if you walk in, you touch a person of age 18? Well, that's 3/7. What does that mean? It means that if you repeat this experiment many times, 3/7 of the times, that's 42.8, no, 3/7 fraction of the times, 3/7 is 42.8. So 42.8% of the time, that person will be aged 18, okay? So the perspective on probabilities that we would be using is this called frequentist perspective. It means you imagine copies of that experiment, and then you imagine repeating that experiment, and you count how frequently the outcome of that experiment was a person of age 17 years. Okay, in the case of age 17 years, it was 28.5% of the time. That is 2/7. So again, probability that a randomly selected person is aged 17 is given by 2/7. So we say that probability that age equals 17 is 2/7, and that's approximately 0.285 or 28.5%. And this is a frequentist perspective. We imagine mental copies of that experiment. We repeat that experiment bajillions of times, and in 28.5% of those experiments, the person selected will be aged 17. Okay, so then we see that this is probability that A equals 18. This is probability of 19. I'm not going to say A equals, right? The argument of the probability function is 17, 18, 19, and 20. This is probability of 20. Okay. So therefore, we can think of average age as a sum of age times probability of an age. Okay. That's a slightly more advanced way of computing the average. So this is average or the mean value. And so then in general, given a random variable x, random because it can take on random values. It can take on this value, that value, that value. When you point to an x, there's a possibility of different outcomes. You don't always get 17. Sometimes you get 17, sometimes 18, sometimes 19. That's why it's a random variable. Okay, so the mean value or average. I think there is a distinction. I'm not making a distinction between the two. Is given by, this is just a notation for the mean value. X times probability of X summed over all possible values of X. Okay, so let's see. Let's sum up probabilities. So, by the way, let's see, probability of 15 plus probability of 17, probability of 16 is 0, plus probability of 18 plus probability of 19. We only have 15, 17, okay, equals 1 over 7 plus 2 over 7 plus 3 over 7 plus 1 over 7, which is what? 3, 4, 5, 6, 7 over 7 equals 1. The sum of probabilities always adds up to 1. Physically, this means that there's a probability that the person that you select is 15, probability that 17, probability that they're 18, probability that they're 19, but the probability that there will be a person is 100%. Okay, so it might in 14.2% of the cases it will be person age 17. In 28.5% of the cases will be a person of age, sorry, in 14.2% of the cases, person of age 15. In 28.5% of the cases, will be a person of age 17. In 42.9% of the cases, or 0.2.8% of the cases, will be a person of age 18. And in 14.2% of the cases, will be a person of age 19. But those percentages must add up to 1. The sum of probabilities is 1. This is called normalization. Okay, so this is called normalization. I.e., the probability distribution is normalized. Normalized means it adds up to 1. So a proper probability distribution will always be normalized. The sum will always add up to 1. I can also compute mean value of a squared. I don't know why I would want to do that, you will see, but I can do that. So mean value of a squared is a squared times the probability of a. I can also compute the mean value of a cubed. That's given by a cubed times the probability of a. I can compute mean value of any function of h. That's given by this expression. It's a little bit abstract, but I can do that, okay? Okay, so you are seeing the pattern. So in general, I can define something like that. Now, so let's say I have some kind of a probability. So by the way, let's go back to this distribution. And it's always a cool idea to mark off the location of the average. By the way, in this case, in this particular case, I forgot to tell you what the average is. In this case, the average, just a second, comes out to be, so if I crank this out, I get age A equals 17.42. Let's see, so it's a little bit like somewhere here, okay? So when you look at the distribution, it's almost like a center of mass. It's not almost like, it is if you actually designed physical distribution by making brass bars and you place them on an axis. That's the center of mass. It's like the center of mass of the distribution. Okay, so that's the average value. Let's say if I gave you another distribution. Let's say if I gave you some kind of a distribution, example 2, and I'm just going to draw it. Okay, I'm going to make a drawing. So this is n, and this is p of n. I'm not telling you what that n is. And let's say it looked something like this, this, maybe lower, then higher, then lower, lower, maybe a little bit higher, then lower, lower. Let's say there's a factory, and in that factory, this is a probability distribution of ages of people in that factory. Okay? And I ask you, well, where's the mean value? And you kind of like eyeball and say, mean value is like maybe right around here. Okay, so it doesn't have to be to coincide with the point of largest value, but this is maybe mean value here, mean n. Okay, but that's not the only thing I can ask. I can ask how broad is a distribution, right? So let's say I have this, and I have another factory where the mean value, the average age, is the same, but most of the people are just of that age, and maybe there are a few people of a similar age. Right, maybe there's a boss right here, and then there's an apprentice, and that's it. Okay, so you see both of these distributions have the same mean value, but they're not the same distributions. Okay, so same n. And if I ask you, what's the difference between these distributions? In plain English, it's important to keep to not lose track of plain English. Well, first of all, the mean value is the same, and the sum of p of n is also a 1, right? So, so mean value equals n times p of n, and this is, let's say that this is p1 and this is p2. They're different distributions, right? And n equals here, and p2 of n. And what we're saying is mean value of the first distribution equals mean value of the second distribution. And by the way, the sum must be equal to 1. And by the way, the sum of p2 of n must be equal to 1. They're normalized. All distributions have to be normalized. Okay, both of these distributions are normalized. Both of them have the same mean value. And now you tell me the difference is that, think about it, like how would you explain to your kid sister what's the difference between the two distributions? The difference is that the first distribution, P1, is wider, it's broader, okay? So how do you, okay, so, but P1 is broader than P2. Notice that if I plotted P1 and P2 on the same axes, right? What would happen is I'm not going to draw those bars. It would get messy, but I'm just going to draw something like this is P1 and this is P2, right? So this is P1, sorry, this is P1 and this is P2. Because both distributions have to be normalized and P2 is narrower than P1, necessarily it has to be taller at the highest peak, because basically where we're going towards is the area under the two distributions is the same, namely 1. So if one distribution is narrower, it has to compensate by being taller. Okay. So for example, this could be something like 30, and this would be something like 100. Okay. So this is a narrower but taller distribution. So P1 is broader than P2. And if you plot them on the same scale, it would look something like this. And question is, how do you quantify the broadness, the breadth of the distribution, the width of the distribution? So the center of mass of the distribution is the mean value. How to quantify the width of the distribution? Okay. And the answer is, it's called a standard deviation. And here's the procedure. So first, let me define the standard deviation. So this is called sigma. Oftentimes they use letter sigma. And it's given by the square root of the average of the deviation Okay. This is a mouthful, but so let's digest what it is. Let's try to understand what it is. So this says, well, you have some kind of a probability distribution. You found its average, its center of mass. Then what you're going to do is you're going to look at this is a sum over a's. You're going to look at the deviation of a value from the average. So here's a value, and here's the deviation. Here's another value, and here's another deviation. Here's another value, and here's another deviation. So that's what a minus a bar represent. If I ask you what is the average of those deviations, you're going to tell me it's 0, because sometimes the deviations are negative, sometimes the deviations are positive. So although it might be tempting to compute the average of the deviation, that average is 0 because it's the deviation around the mean. So sometimes the deviation is positive, sometimes deviation is negative. But if we compute the average of the square of that thing, okay, that would not be 0 because the square of the deviation is always between 0 and some positive number. Okay, so this thing is the average of the square of the deviation. And then we take the square root because, well, we looked at the squares of the deviation. We're really interested in the deviation. Okay, and so then you take the square root. Okay. Now the quantity if I ask you, what's a shorthand notation for this quantity right here? Right. Go back to this thing right here. It's the mean of the thing that sits here. So this is really just the mean of this, right? So I'm saying, okay, I computed the mean of the function, the mean of the the mean of the distribution, and I'm now going to compute the mean of the squares of the deviation from the mean of the distribution. It sounds worse than it really is. Okay, so I'm looking at all the deviations, I'm squaring the deviations, and I'm going to compute the average of the squares of those deviations. Okay, this is called variance. Okay, and I guess it's represented by sigma squared sometimes. So standard deviation equals the square root of variance. Okay, note that average value of a minus a bar quantity squared equals, I'm going to just distribute this whole thing, a squared minus 2a bar plus a bar squared, which is a squared minus, well, a bar is a number. Okay, so if you were to compute the average of this kind of a product, the a bar goes outside the sum. And so you will find that this is a bar quantity squared plus a bar quantity squared. And so this comes out to be, a squared bar minus a bar quantity squared. Okay. If you're not completely clear on how I made the step from here to here, actually write out, right? So you just compute 2a bar p of a, and then you will convince yourself that this equals 2a bar quantity squared. Okay, I'm not going to do that. Okay, in our case, so let's say that this is called sigma squared. Sigma squared comes out to be 1.30 38, and I'm asking you to check it. Okay, so to do that, what you have to do is you have to say 17 minus, what is it, 17.2, what was the average, minus 17 point, no, so it's 15 minus 17.42 squared times the probability of, actually, you can do it even more primitively, right? So if you want to check this, I'm asking you to check it, right? So how do you calculate that? Well, it's the average of all these deviations, right? So what are the deviations? Right, so you have 15 minus 17.42, you have 17 minus 17.42. Okay, so this is times 1, this is times 2, then you have 18 minus 17.42, that's times, there's 3 of those, okay, there are 3 of those, so you don't get confused, I will just say this. Oh, I don't know what's going on. I think, okay, 1 of those, so 2 of those, okay, so there's 3 of those, And then I have 19 minus 17.42, one of those. Okay, I'm asking you to actually do this computation. That's what I'm writing out what's underneath the hood of those computations, right? And so what you would do is you would say 15 minus 17.42 times I guess 1/7 plus 17 minus 17.42 times 2/7 plus da. Actually, I'm asking you to compute the squares of these, right? And that will give you the variance. Or you can do even more primitively. Instead of multiplying by 2/7, you can say 15 minus 17.42 squared plus 17 minus 17.42 squared plus 17 minus 17.42 squared plus 18 minus 17.42 squared plus 18 minus 17, and so on, all divided by 7, right? The most primitive way. You can follow this same recipe as here, or you can be a little bit more sophisticated and follow this recipe. But before we actually looked at the average of the age, now I'm asking you to compute the average of the deviation, average of the square of the deviation of the age away from the mean. Okay, in any case, when you take the square root, it's 1.38, and that comes out to be 1.17. And that's kind of a measure of the width of the distribution. Let's look at the distribution. So this says that the width of the distribution is 1.17. Okay, and it's about right here, right? So this is about, so sigma equals 1.17. That's about right. Plus 1 to the right, minus 1 to the left. And then there's some tails, but the meat of the distribution is within this range. That's what the standard deviation means. It's a measure of the width of the distribution. If I look at these distributions, here's the sigma, and here's the sigma. You see? So you can see that the width, this is sigma 1, and right here is sigma 2. Okay? Let's now go to the continuously. So these are ages of people in factories, in a room. They come in discrete values. Yes, it's true that the age is also continuous. It can be 17.1 years, 17.8, and so on. But normally, when we think of age, we think of a discrete value. But what if I have something else? What if I play the game of darts and I try to shoot a dart at a bar, like a linear bar? It can hit, the dart can hit anywhere between the left end and the right end. So now it's a continuous distribution. And so now I can talk about location where the dart landed. Okay, so here's my bar. So this is, so x equals 0, and let's say this is x equals 1. It's 1 meter long. And if I am an okay shooter, I would get something like that. So outside the probability is 0, right? So let's say I'm like that. And here's if I'm trying to hit the center, okay, so this is the bullseye, then maybe a better distribution, a better shooter would have a distribution that looks like this. Notice the distribution has to be normalized to 1. And so because the second distribution is narrower, it has to be taller. Okay, so normalization one is between x minimum and x maximum of p of x dx. Now this becomes an integral. Oftentimes, there are some common applications where x minimum is minus infinity and x maximum is plus infinity. How would you define the mean? By the same formula as before, only now you replace sums by intervals. So the moral is, to go from discrete to continuous, you replace sums by integrals. But there's a little bit of a caveat. So what does this distribution mean? Before, it was a discrete. I could say, what's the probability that a person's aged 17? What's the probability that a person's aged 18? Now, P of x is not the probability of x. Okay. Instead, what this means is the following. P of x dx equals probability that a random variable lies between, well, this sort of depends on the definition, but let's say, to make it symmetric, between x minus dx over 2 and x plus dx over 2, right? So I have a distribution, and here's a value of x, and the area here, P of x dx equals area of this bar, is a probability that the dart landed within this region. That's the meaning of continuous probability distributions. Okay, that's just what it means. The probability that the dart lands somewhere is the area under the whole curve, and it's always normalized to 1. Okay, the probability that a dart lands to the left of the peak is the area between 0 and the peak. The probability that the dart lands to the right of the peak is the area between the right and between the peak and the right edge. The probability that the dart lands within this region is the area under the dart, is the area under the curve within that small region. And as the region gets smaller and smaller, we can approximate it by this rectangle, the usual stuff. So therefore, it makes no sense to ask for probability of landing at a particular location. It's 0. You can ask, what is the probability of landing within a small range of x around that x? That's a meaningful question. The answer is, it's P of x times dx. Okay. So let me give you a quick example, and I want to save a little bit of time to talk about physics today. So example, and let's say income distribution. It's not a very good income distribution. P of x equals a e to the minus x. First, e to the ax, e to the minus ax. First of all, what does it look like? X is income. And this is probability, right? So you have a country, many people. And so what does it mean to say that this is the income distribution? It means that if I look at some particular value of the income, say this is, I don't know, $30,000. Then P of 30,000 times delta X and let's say delta X equals $10. That gives me the fraction of the population whose income is within $10 of the $30,000. The fraction of the population okay, that's what it means. First, let's check normalization. And the reason I said fraction is because this distribution is normalized to 1. If you want the number of people, not the fraction, but the number of people with an income within $10 of $30,000, you have to multiply this number by the total number of the population. So if you have 100 million people, the number of people with income within that range is 100 million times this fraction. Okay, so check normalization. Okay, so a e to the minus ax dx between 0 and infinity. So let's say income can be between 0 and infinity equals a between 0 and infinity e to the minus ax dx, which is a times e to the minus ax over minus a from 0 and infinity, which equals to a times e to the minus infinity 0 minus 1 over minus a, which equals to 1. Okay? And it should be. And I will leave it as an exercise for you to check. Oops. I will leave it as an exercise for you to check that average income for this distribution equals 1 over a. Average of the square of the income equals 2 over a squared. The variance equals, well, a squared minus a quantity squared equals 1 over a squared. And the standard deviation, therefore, is 1 over a. Let's see. So this is an exponentially decaying distribution. The scale of the decay is 1 over a. In other words, the length or the x during which the distribution falls off by a standard amount e to the minus 1 is 1 over a. The mean is indeed exactly that value. So here's the mean. And the width of the distribution just a second, is also 1 over a. So not most, but an appreciable fraction of the population will be located here, okay? It's not always that 70% that maybe you have heard of. That's for a specific distribution called a Gaussian distribution. We will talk about that distribution at some other time. This is an exponential distribution. Okay, so you can calculate what fraction of the population has income within this range. Okay, so that's between 0 and 1 over a of a e to the minus ax, x. And I'm not going to waste time, so I'm going to pause. I'm going to do that calculation, and I'm going to write down the answer. And the answer is very interesting. It's e to the minus, okay, so e minus 1 over e. And when you substitute the value of e, that comes out to be about 63%. So 63% of the population have that kind of an income. Okay, good. And that completes the mini lesson. Probabilities, we'll use them and you will understand what you need to understand better. I just wanted to give you just the basics. Okay, thanks.